Alright guys, so this is our second video, and in this video we're going to look at hyperbolas, which is the conic section that we didn't get to in our last class before break. So we're going to start with the definition of a hyperbola that is the locus definition, or the definition of a hyperbola as a collection of points. And we're going to say that the hyperbola is the set of all points whose distance from 2 points, the foci, have a constant difference. So here again we've got 2 foci, just like the ellipse. In general, right here, we're going to say that the foci are located outside the hyperbola. And when we talk about a constant difference, what we're going to say is that that constant difference could be a positive or a negative. So we're going to take a quick look at this on our program right here, and then we will jump to starting to define our hyperbola graphically. So right here, we're going to say that our first foci has the distance of L1 from our point on the hyperbola, and our second foci has a distance of L2 from our point on the hyperbola. So right here, L1 minus L2 is going to be a length of 9 for L1 minus a length of 1 for L2, giving us a constant 8. So right here, what we're going to say is, as L1 gets longer, L2 has to get longer to compensate for L1 getting longer, so that our difference remains 8. And right here, what we're seeing is the relationship between those distances, giving us points that sort of get further and further, creating one side of the hyperbola, right? Now right here, if we go over to the other side of the hyperbola, right here we can see now that L1 is the shorter length, L2 is the longer length. We're going to say L1 in this case is 1, L2 is 9, and right here we've got the negative of that constant, right? On the other side it was a positive 8, here it's a negative 8, and again what we're saying is as L2 gets longer, L1 has to get longer to compensate as well, giving us this side of the hyperbola. Okay, so that's the locus definition. Now in general right here, we're touching on the locus definition to sort of connect it to the rest of our conic sections with regards to the conic sections as shapes. But in general, when we define this graphically, we're really going to look more at the conic itself to define the shape of the hyperbola. In general, what we're going to say is the hyperbola can be defined by 2 diagonal asymptotes that are diagonals of a box. So the hyperbola has 2 vertices, and those vertices are the points on the hyperbola that minimize the distance of the foci from the hyperbola. So right here we've got our first vertices and our second vertices. Right here what we can say is that 2 sides of the box that give us the diagonal asymptotes are going to go through those vertices, and then the other side of the box obviously connects the sides that go through the vertices. So right here, this box is basically defining 2 diagonal asymptotes that will give us the sides of the hyperbola that go through the vertices, right? So our hyperbola goes along the diagonal asymptote through the vertices and then goes out on the other diagonal asymptote. Now, right here, if we take a look at the hyperbola as a conic section, we basically have this shape right here. And if we take our conic and face it, we can basically see our hyperbola as these 2 open shapes, right, that go along the sides of the conic. And as the conic gets wider and wider, the sides of the hyperbola get wider and wider. And really what we're seeing here is those 2 diagonal asymptotes defining our hyperbola are actually the sides of the conic. And right here, the box that is sort of giving us those 2 diagonal asymptotes graphically is really made up of the width of the conic, where our plane begins to cut the top cone and the bottom cone, and the distance between the vertices, which basically is the distance between where the cut of the plane begins to intersect with the conic itself. Now right here, we're going to define the lengths that define this box as accesses of the hyperbola. Right here, we're going to say that the transverse axis is the distance between the two vertices, and that's going to be this length right here, 2a. And so right here, we'd say that that transverse axis is 2a. And we're going to say that the conjugate axis is basically the width of the conic where the cut of the conic section begins. So that's going to be this length right here, and that's going to be our 2b. So right here, if we go over to our hyperbola on our graph, we would see this length as 2b and this length as 2a. And right here, we can say that the distance from the center of our box to our vertices is a length a, if the distance between the two vertices is 2a, and the distance from the center of the box to the top and the bottom of our box here is going to be a length b, since that whole side of the box is 2b, right? Oh, so we should write that 2b down here too as well. All right, so right here, we would say, of course, that the focal axis is the line that goes through the foci. And in general, right here, what we can say is that just like an ellipse, we have a Pythagorean relation for the hyperbola. And the Pythagorean relation for the hyperbola goes like this. Within the box that defines our diagonal asymptotes, we can get a right triangle right here, where the two shorter sides are b and a, and the hypotenuse of the right triangle is going to be the length c, which is actually also the length from the center of our box to the foci. So right here, just like the ellipse, we would say that the distance from the center to the foci is c, and the distance from the center to the vertices is a. But now that length c is longer than that length a, since the foci are outside of the vertices. Right here we can say then that the Pythagorean relation we have for a hyperbola is a squared plus b squared equals c squared. Now we're going to define the asymptotes later in class. For right now, we're basically just going to say they're the diagonals of the box, and we're going to use them to graph the hyperbola, but we're not going to define what they would be as lines, right? So right here, we're going to go on and talk about the equations for the hyperbola on the xy axis. We're going to say that the hyperbola as a conic section on the xy axis with center hk is defined horizontally as x minus h squared over a squared minus y minus k squared over b squared equals 1, and vertically as y minus k squared over a squared minus x minus h squared over b squared equals 1. So right here, we're going to say that a horizontally orientated hyperbola is basically going to have the two sides of the hyperbola open horizontally, and vertically orientated hyperbola is going to have those two sides of the hyperbola open up and down, right, vertically. Now right here, what we're seeing is that the first term determines whether we're orientated horizontally or vertically. If our first term is an x term, then we're opening horizontally. If our first term is a y term, then we're opening vertically. The thing that we want to take note of is that it doesn't matter whether a or b is larger. So in the case of the hyperbola, it could be that a is larger than b, or we could have b larger than a. It doesn't actually matter. With the ellipse, we would basically say that the orientation, horizontal or vertical, is determined by the larger denominator. But here we're saying it's determined by the first term, or the positive term. So we're going to look at graphing the hyperbola from an equation. So right here, we're going to graph A together, and I'm going to let you guys graph B on your own. With A, we can see that our first term is an x term, which tells us that our hyperbola is going to be horizontally orientated. And right here, we can say that the center of the box that's going to give us our diagonal asymptotes is going to be -3, 0. Our first term is going to have a denominator of a squared, so a squared is 9, which means a is going to be a length 3, and our second term is going to have a denominator b squared. So if b squared is 4, we know that the length b is going to be 2. Now right here, what we're going to do to graph the hyperbola is graph the box from the center, and then we're going to graph the diagonal asymptotes through the box and give the two sides of the hyperbola going along the diagonal asymptotes through the vertices. So right here, we're first going to graph the center. We're going to say that the center of the box is that negative 3, 0. And right here, since I'm horizontally orientated, I'm going to go out that length of A to my two vertices. So right here, I'm going to go out 3 to my two vertices on the horizontal sides of my box. And now right here, I know that B is 2, so I'm going to go up 2 and down 2 to the ends of the conjugate axis. Now right here, I can graph my box through those points, through the vertices in the top and the bottom of the conjugate axis. Now right here, I'll graph my two diagonal asymptotes. Now I'm going to give myself some points here. I know that the asymptote is going to be a line, so I can basically sort of use the slope that I get from the center of my box through the corner, which is going to basically be a positive 2/3 for this diagonal asymptote, and a negative 2/3 for this diagonal asymptote. And then I'm going to graph the hyperbola along these asymptotes through the vertices. So the right side of my hyperbola is going to go along the asymptotes through the vertices on the side of the box, and then out along that second asymptote. And then right here, the left side of the hyperbola is going to come through that vertices and then out along that second asymptote. So there's a graph of the hyperbola. Now, all of our dotted lines aren't really the graph of the hyperbola. The graph of the hyperbola itself is what we've drawn with that solid red line. And in general right here, while we would graph the hyperbola by first graphing that box and getting those diagonal asymptotes, in the end you might not represent all of this when you're graphing the hyperbola. Now, next what we want to do is graph the foci, and we can get the foci with the Pythagorean relation of the hyperbola. So we know the Pythagorean relation of the hyperbola is a squared plus b squared equals c squared, and right here I've got a squared as the denominator of my first term, so that's going to be 9, and then I've got b squared as the denominator of my second term, so that's going to be 4, and right here that gives me c as the square root of 13, which is approximately 3.6. So basically I can go out a length of 3.6 from the center and get these 2 points approximately, which are my foci. That's graphing this horizontally orientated hyperbola. And what I want you guys to do is to graph this second one on your own. Now, because the first term is a y term, we can say that this is a vertically orientated hyperbola. So instead of going out horizontally to our vertices from the center, we're going to go up and down to our vertices from the center. What I want you guys to do is to give this one a shot on your own, and we will come back and look at this together in a second. All right, guys, so right here, we know it's a vertically orientated hyperbola. We can pull the center as 2, 3 from our equation, right? We're subtracting 2 away from x and subtracting 3 away from y. Right here, we know that 16 is going to be our a squared, so that means a equals 4. And 25 is going to be our b squared, so that means b equals 5. Vertically orientated, so that means we would go up 4 and down 4 to our two vertices. And then we're going to go out a length of 5 to the other two sides of the box. So right here, going out a length of 5 gives us the ends of that conjugate axis right there. And right here we can draw our box through those points and then draw our diagonal asymptotes. And then right here, our vertically orientated hyperbola is going to go along those asymptotes through the vertices on the sides of the box and then follow the other diagonal asymptote out. So that's the graph of the hyperbola. Now, foci of this hyperbola, we're going to have to use that Pythagorean relation to get. So right here we would say a squared plus b squared equals c squared for that Pythagorean relation. So right here we've got 16 plus 25 equals c squared, which gives us c as the square root of 41. and we can say that that length c, which is the distance from the center to the foci, is approximately 6.4. So there's our center. Now right here, we're basically going out 6.4 vertically. So right here, our top foci is actually off our graph, but our bottom foci we can plot right there at basically something that is close to 2, negative 3.4. So that's our vertically orientated hyperbola. We'll get more practice with this in class on Tuesday, and I'll see you guys then.